All right, students, I'm moving along here grading, and I thought I'd take a little break from grading and make you a solution guide. I think this will help you kind of self-grade it, especially you guys online, because when you're online, I can't really write on your tests and give much feedback, and so I think this video is the replacement of that. So please watch it and watch in detail. I would even encourage you will probably get this before I get done grading, so you can do kind of a self-check, if you will, or a self-grading, see how you did, and then kind of get an idea of any weak spots you might have, and maybe even go over your exam. All right, let's run through these 5 here. It's here. The first one says we have 3 charges on the corners of an equilateral, and I'm sorry about that. That should be equilateral. Equilateral triangle with sides of length 10 centimeters. So I'll just put a little 10 centimeters in there, and maybe I'll just point out that if it's equilateral, it's also equiangular. So they're all 60 degrees. What is the net force on this top charge? And so the general idea was to find the electric field first, from that multiplied by the charge, and so that's going to be this 7 microcoulombs, and then multiplied by the electric field that's created by these other 2. And so let me start there. And so the electric field, what we might call net, would be the electric field. I'll call this number 1 and number 2. So it'll be the electric field from number 1, and add to that the electric field for number 2. Maybe it's worth drawing a picture, because a lot of these problems, we can do a big piece of it by the physical picture and save ourselves a lot of work. That was my argument about symmetry. That was an important piece that you probably won't have time if you just rely solely on math. And this is a good example of that, because if you look at the electric field from a positive charge at the place where you have this 7 microcoulombs, it would be directed radially outward. And then likewise for the number 2, it would be directed radially inward. And when I say radially, I mean towards that negative one. So this is going towards the negative one, the one making the field, and this one is going away from it. So I want to know the field at this point from this one, and also at this point from the second one. And it would look something like this. And so hopefully the first thing you kind of notice, if you draw a horizontal and vertical line, maybe representing the x and y axis, you will begin to see that these 2, and maybe I should put the equation of the electric field from a single point, would have the same magnitude. They each are coming from the same magnitude of charge, and they are each the same distance away, and hence they're the same size. And not only are they the same size, but their angle from the x-axis is each this 60 degrees, if I kind of do corresponding angles here and maybe alternate interior angles here, and using a little geometry. And so because they have the same magnitude and they have the same angle, and of course one is angled up and one is angled down, the y components would cancel off. And so you can begin this by saying the net electric field in the y direction is 0. Which I guess then you could also come back to this equation and then say the total force in the y direction, which would be the charge times the field in the y direction, which we just said was 0, will come out to be 0. And so this 7 microcoulombs times 0 gives you a 0. And so you might argue we're halfway done. And that's the nice thing about the symmetry here. I really haven't done much work, and yet right away, and hopefully you're not talking to yourself like I am here during the exam, but within maybe 10 seconds or so, you're halfway done with this problem. You said, okay, well, the y direction is 0, the electric field and the force. Now, also, hopefully, the other thing you get out of this is that, again, looking for the net field, which we now know is only in the x direction, you can kind of see it would be double the field from just one of them. And so both of these would have a positive x component, and both of them would be the same magnitude. So that makes, again, the problem a little bit easier, because now, instead of finding x and y of all of them, I only have to find x of one of them. And that, would have been much harder if I had to do 4 individual pieces, x and y of both, versus just x of one of them. So that's the real advantage of understanding and seeing the symmetry there. So now let me go ahead and then put the equation for the electric field. That's the magnitude here. And then to get the x component, I would go cosine of 60 degrees. And now to get a number, I'll put in my values. And Coulomb's constant is about 9 times 10 to the 9th. The charge making the field is the 3 microcoulombs. The distance away in meters is 0.1 squared. And I know I didn't put my meters units in this equation, but again, this is in meters and in coulombs. So we need to make sure our charges is in coulombs and our distance is in meters. And then cosine of 60 is one of those easy ones. It's 1/2, and that actually simplifies a little bit there. So grabbing my calculator, 9 times 10 to the 9th, multiplying it by 3 times 10 to the negative 6, and dividing it by 0.1 squared, comes out to be 2.70 times 10 to the 6. And again, putting in my units as meters and coulombs, this would come out in newtons per coulomb. So there's the value of the electric field. So the final step here would be then the force in the x direction would be the charge we're going to put there at the field in the x direction. And so it would be the 7 microcoulombs times this 2.7 million newtons per coulomb. And so times 7 micro. And we're looking at about an 18.9 newtons in the x direction. And that's probably good enough right there, because I did list the x and the y. You don't need to kind of add anything more to that. All right, well, I hope that first one went well. That was supposed to be kind of the straightforward one, and one that you could hopefully pound out within 25 minutes so that you felt like you were kind of ahead of the pace, because some of these are longer, but some of them are kind of short too. And let's take a look then at number 2. So number 2 says we have a very long charged cylinder, radius capital R, has a charge density per unit volume. A is some constant, and probably is worth pointing out that this A is some constant. It doesn't represent the area, because as we sit down to do this problem, it says, what is the equation of the electric field inside of the cylinder? And it hint uses Gauss's law. So I will start A with Gauss's law and recognize that we use a capital A for area in Gauss's law. And so please don't confuse that with that A. That A is just some other constant. So maybe I should have chosen a different constant than the A, because that could get confusing. But looking at the ones I've graded so far, I can see that there were a few people confusing that, but only a few out of all 100 plus of you. So that's a good sign that it wasn't really much of a confusion. Of course, then the other half of this is the charge inside over epsilon naught. Okay, and this could be the tougher part of this problem. So following the hint and starting with Gauss's law, I'll draw a Gaussian surface, and hopefully this looks a lot like you saw me in class, as well as the book, drawing a Gaussian surface and making the following arguments: that if you take the dot product, you get EDA, and you get cosine of some angle. And again, a good choice of a Gaussian surface, we would say that the charge looks the same no matter where you are on the Gaussian surface. Some is in front of you, some is behind you. And because the equation of the density is the same in terms of R, in other words, it's symmetric with R, they would look the same all over the surface. That's not to say it's equally distributed, but it would look the same. And so whatever the electric field is would be a constant, and that's how we pull it in front of the integral. We also argue these are lines of symmetry, again, because of that. So this comes out to be 0 degrees. In other words, we know the electric field must be along lines of symmetry. And so using and invoking those arguments, we get something that looks like this. Where we just have the integral of dA. And that's the area of the Gaussian surface. So if you imagine drawing this Gaussian surface with a radius of, say, little r, not to be confused with capital R, this would then be the circumference around it, and then however long you draw the Gaussian surface. So maybe it would look something like this if I kind of imagine the Gaussian surface, kind of like this, okay? And so here's my Gaussian surface. So the circumference here is 2 pi r. That's how you get the area if you kind of imagine unrolling it. It's that, and then times its length. So that is what you would get if you actually did that integral. But we're not even going to bother to do it, okay? So there would be the left-hand side of the equation for Gaussian surface. Now, just to make it clear, and again, you saw me do this and the book do this, the surface area of what you might call the left edge and the right edge of the Gaussian surface actually come out to be 0, because we argued from the symmetry that the electric field is radially outward. And so the angle would be 90 degrees for what I often call the caps of the cylinder. And this would be the left cap and the right cap. And so I didn't even kind of include those here, but I did want to point out that, you know, it was in my mind. I was thinking about it here. And so I didn't just ignore it. This is not a Gaussian surface that stretches out for forever. Although I guess we could make that argument. Although it does say we have to have a closed surface. So at some point we've got to put a cap on it to have it justified. But again, this is no different than what we did in class so far when we had an evenly distributed charge. Here's where it becomes a little different than in class. We have a density that changes. And so let me come off to the side and calculate this. How much charge is enclosed in my Gaussian surface? And maybe the place to start is to say, well, I'm just going to think about adding up a little bit of pieces of charges that are in here. And if you add up all the pieces of charges, I like to call them chunks of charges, you add them all up, you get the total that's in here. And so imagine me taking an infinite number of dots, each dot representing a chunk of charge, and I'm going to add them up, okay? Well, that's where this idea of density comes from. Density, of course, is how much charge do you have in a little bit of volume, okay? And that's where I will substitute then a little chunk of charge for the density at that location times the volume. And so again, in my mind, I've got these little dots, these little chunks of volume that I'm adding up. So I'm going to add up all these volumes multiplied by the density there, the charge density, and that's going to be the charge. That right there is this, the charge at that point, and then I'm going to add up over the, or inside of all the Gaussian surface here. Now here's why you want to be careful. This does not equal to just density times the integral of dV. That would be true if the density was a constant. And when we did it in class, and your book did an example like that, like your book did an example where it was constant and where it was non-constant. So this is non-constant. So you can't do this step. And it's too bad, because then it would be just density times volume. And the volume of that Gaussian surface would be this area which would be pi r squared times its length, and then I would just put that in there and then move forward. But that's going to make a mistake there. That's assuming you have the density. That would be the same as, saying that the density is the whole charge over the whole volume. And that's not quite true. The whole charge over the whole volume is equal to the average density. And if it's uniform, then average density and density are the same. So I better make sure I put a negate sign there. We don't have a constant uniform density here. So I can't do that. Okay, but what I can do is I can then actually put in the equation for the density and then start to do the integral. And then here I can realize that if I'm looking at the volume I'm making of a Gaussian, the volume within this Gaussian surface, I could say, why don't I think of this as just a bunch of shells wrapped together? So I would take the volume of this shell plus the volume, maybe I better roll it this way, plus the volume of a second shell, plus the volume of a third shell, and a fourth, and a fifth, and a sixth. And so hopefully you're getting this idea that I don't need to waste another stick it to kind of show you, but I'm going to then say, here's what I'm thinking in my mind, that I need to take the volume of one of these cylindrical shells. And so maybe looking at it, I'll say, okay, it's got a certain thickness as it goes back in here. And take the volume of that shell, and then the volume of another shell on top of it, and another shell, and another shell. And the reason that is important here is because the volume of one of these, so if you kind of unroll one of them, you would say, well, what's the volume of this piece of paper? And you would say its length times its width times its microscopic thickness of it. So if you go back to imagine it rolled up, its length would be its circumference, 2 pi r. And here would be the length, and the thickness of it, so I'm going to be adding these up, moving out, would be like a dr. And so I'm just going to do the addition here by imagine starting at the first one with a radius really, really small, 0, and adding them up until they get bigger and bigger, and eventually they're going to get to capital R. And then fortunately, mathematically, this is not a hard integral. I can factor out, factor out is the right word. Bring out an a in front of the integral, bring out a 2 pi in front of the integral, bring out an L in front of the integral, and notice then that I have r to the third power. So if I integrate r to the third power, I'm going to get r to the fourth over 4, and from 0 to r makes an a 2 pi L, an r to the fourth. Oh, sorry, my mistake. I got careless here. Let me pause. This is the charge inside the Gaussian surface. So I'm not trying to find all the charge of the cylinder. I'm just going to add up until I get to the Gaussian surface, and that would be little r. Of course, this might get confusing, so maybe it would look better if I put r primes here. And so I'm imagining starting at a This is my variable, small radius r prime, and it gets bigger and bigger until I get to the r of the Gaussian surface. And so my integral might have a prime right here and evaluated from 0 to little r. So this would be pi, a times 2 pi times L, and then this would be r of the Gaussian surface to the 4th power over 4. Now, and again, that's important because it matches this little r on the other side as well as the L. And so I'm going to put the A, I'm going to put the 2 pi, the L, the r to the 4th over 4. And then cancel off a 2, and cancel off a pi, and cancel off an L, and even cancel off one of the r's. So finally I get to what I was trying to solve for, and that is what is the equation of this electric field. And let me not forget to do the epsilon naught down here, because this is what I solved over here was just the charge inside. All right, and then I have the 4 epsilon naught. And so there should be the value of the electric field somewhere within there. Now, by the way, we don't have to do it, but if it was asking for the field on the outside, of course, that's where this capital R would have came into place, and I would have added up to capital R and stopped, and I wouldn't have kept going to the edge of the Gaussian surface because the charges don't keep building up, and so I'd have a little r on this side and a big R on that side. And we saw some problems like that, but that's not what this one is, so let's not, take time during the test to try to solve that one. But we got our answer. Now we can go on to B, and then B, there's kind of a couple ways we can do it. Maybe a little math review is important just to begin with, because it says here, what if a scientist or engineers wanted to actually construct, a cylinder like this? But here's the goal of the construction. It is to make a constant electric field inside. Now, by the way, you hopefully remember that when we did the electric field on the inside with a constant density, we did not get a constant field. So maybe I should say if the density is equal to a constant. So we got an electric field that was not equal to a constant. In fact, we got the electric field was proportional to the position R. Maybe I should look it up. Well, let me not take the time to look it up or talk about that, but I would encourage you to look at chapter 24 in the Gaussian surface. And they did this one if you had forgotten. And they said it was proportional to R. And in fact, when you were outside, then it was proportional to 1 over R. And so it looked something like this if I plotted electric field with R. Now, again, during the test, I wouldn't take the time to maybe graph all this, but it might be good to think about it, noting then that I should not be looking for a constant density. I'm looking for a constant field. And that's the question. What kind of charge density would you need in order to form a constant field, not a constant density? In fact, I know I said I wasn't going to look at it, and I know time is always important during an exam, but I just can't help but kind of open the book now and think about Gauss's law. Where did he do a cylinder? Now here's a cylinder on the outside. Here. Yeah, maybe it was an example. Maybe it was a homework one. Okay. All right. So I guess I won't be showing it in the book. But that being said, let's just focus on back to the problem here. If you do remember from the homework, again, that should tell us the density is not a constant here. Now I've kind of ran myself out of space, so maybe I'll use the back edge of problem number 1 here and just kind of keep reminding you what I'm trying to get. Now, one way to do this might be something like this. I gave you a hint that the density would have this form, so it would be what we call a power function. It would be the constant a raised to some power n, and that's the question here. What would this exponent be? What would be its value? And this is where I was starting to do this problem and saying, well, you might want to think about what do you mean by a constant. In other words, if I had y equaling x or y equaling x squared, and I put this on your traditional xy grid, the square looks like a parabola. The proportional one looks like a line. Neither of those represent a constant for the value y. What represents a constant would be something that would look like that, which would be y raised to a power of x to the 0 power. So 0 power, of course, means just 1. And I guess if you had a constant a in front of it, this would equal to a. And so what I'm trying to remind you of from your math class is if you are going to say y is equal to some kind of constant, you are really saying y is equal to some number times x to the 0 power. And so we need a 0 power. So in other words, we need an equation that says electric field equals something times r to the 0 power. And one of the ways, almost too easy of a way to solve this, is to go back and realize that for the density that was given in part A, r squared, we got an electric field that is r cubed. And what we are trying to achieve in part B is r raised to a 0 power. So this is 3 powers too big. And so that would mean that our density distribution is 3 powers too big. And so we have a power of 2. And so if you take 3 away from that, so 2 minus 3, you get a -1. So I'm thinking that if I had a density that equals to a r to the -1, that means n equals -1, it should work. And so I guess I'm done. However, maybe it's worth going through these same steps here that we did in A. So I guess it would look something like this. You would start with Gauss's law. And on this side of the equation, I would basically get everything the same there. And so this would be an e2 pi r l. And the other side of the equation would be very similar, except for right here. Maybe I'll grab a colored marker here. But right here, I would have a power of n. And so when I get to this step right here, for the charge enclosed, I would have this integral from 0 to r. So right here, 0 to r. Then I would have the a, and I would have this r prime to an nth, and the 2 pi r prime, the l, and the dr prime. So I'm just recopying this step, but putting an n right there. And hopefully what you'll see is everything will transfer down, and I'll have just n's here. And so this right here would be an n plus 1. Then when I integrate it, I get n plus 2. And so the end result here is an n plus 2. In fact, I'll just carry that out. This would be an a, and I'll pull out the 2 pi and the L, and then I would have this integral of r prime n plus 1 dr prime. So when I do the integration from 0 to r, I would get r to the n plus 2, right? You raise the exponent by 1 and divide by the new exponent. So over here on this side of the equation, I would have an a, and I would have a 2 pi and an L, and I would have an r of n plus 2 over n plus 2. All right, and so now when I start canceling 2's and pi's and L's and one of the r's, I would have a generalized equation that said it would be equal to a times r to the n plus 1 over n plus 2. And so you might call that a kind of a generalized solution. And of course you can see that in what we got here for our answer in A, because we had a density that was raised to a power of 2. So n would be 2, and so you add 1 to it, you get a 3. That's what that's saying. Oh, sorry, this one right here, n plus 1. So in part A, that was a 2, and so we got 2 plus 1, and we ended up with an answer of r to the 3rd power. Okay, and then of course downstairs, we had 2 plus 2, which is a 4, and again, that's what we got in A. We got number 4. But in our case, we are trying to get this statement that is saying n plus 1 is a 0, which again would bring back to what we already concluded, and that was n, it would have to be a negative 1. So that could be a tough problem, which is why I put it as part B, so it wouldn't count as too much. Same thing I did in problem number 3. 3B is a pretty hard one, but counting it as half the problems, it's not an overwhelming number of points, so if you don't do it well, you won't get docked too much. That was kind of my thinking on here. Anyways, so that's a tough one and a little different, but hopefully A went straightforward for you. That was kind of the normal thing we did a lot of. B is a little more advanced thinking. All right, let's move on to number 3 then. And maybe I'll look at my pace. If I was taking an exam, I should be about 50 minutes into the test. And so, good. My pace is going well here. So, I'm on track to finish this in time. Okay, so now let's look at this one. And like I just said, 3B is a pretty hard one, but I'll give you a bunch of points for setting it up, and it's only worth 10 of the 20, and hopefully A is a little more straightforward. Mostly because I actually give you the equation for the potential. I don't ask you to solve for it. This is about the conservation of energy one. It begins like this. You hopefully remember from this chapter 25 that the change in internal energy is equal to the charge times the change in potential, which we said equal to negative the change in kinetic energy, and that's how we get our 1/2 mv squared. But let's start here at the harder part of the problem, which is the change in potential. So it'll be final minus initial. And if you come back and read the problem, that says we have a cone, and so I've got this cone here that in part B, I'm going to think of it as a bunch of rings. And fortunately, we don't have to come up with the equation for potential, at least not yet. This is given to us. And so the first step would just say, all right, what is the initial and what is the final? So it says here that the electron starts really far away, and so the initial would be 0 potential. And the final is when it comes racing in and hits the apex here of the cone, and they say that that cone has this for its potential. So it would be the square root of 2 times Coulomb's constant times a Q over the height of the cone. By the way, this is true only if the cone's height and radius are the same, which is the case there. So this is not kind of a general equation. It's an equation for this particular problem. Okay? And then just in case we define these, so K would be Coulomb's constant, Q would be the charge on the cone, excuse me, the charge, and then H would be its height, which would also be its radius in this problem. So I would start here and put in some numbers, and so let me put in the square root of 2, let me put in 9 times 10 to the 9th. In A here, they give me the height of the cone and the charge, and so this is 10 nanocoulombs, and the height, just need to be careful with our units, that the height needs to be in meters. So our change in potential, let's see what we get, would be the square root of 2 times 9 times 10 to the 9th times 10 times 10 to the negative 9th divided by 0.05. And we're looking at about 2,545 volts. Good. And also, kind of remember, the potential is increasing as we get to the apex. So that's good. We know that electrons like to go to higher potential because that's lower potential energy, which is the second part of this. Then let's say, what is the change in potential energy? So we'll take the charge of the electron, the negative 1.602 times 10 to the negative 19 coulombs, and then multiply by the change in voltage we just calculated. And a volt is a joule per coulomb. And so we're going to see the change in the potential energy, and you're going to see it's a negative. That's good. That's a decrease in potential energy, which it should be. Like a ball rolling down a hill will lose gravitational potential energy and gain kinetic energy. And that's what's going to happen here. It's going to come closer, 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 and go faster, faster, faster. Of course, the electron's negative and the cone is positive. All right, so taking that number and then multiplying it by the negative 1.602 times 10 to the negative 19 gives me a negative 4.08 times 10 to the negative 16 joules. Nice. All right, now, again, that has to equal to the negative of the change in the kinetic energy. So the change in kinetic energy would be a plus 4.80 times 10 to the minus 16 joules. And then change in kinetic energy would be 1/2 mass times final speed squared minus initial speed squared. And in this case, they say we start from rest, so that term's going to be 0. So I'm going to need a little calculator work to find the speed. So it looks like I'll take this energy and maybe first multiply it by -1, so I get a positive number here. Then multiply that by a 2. Then divide that by the mass of the electron, 9.11 times 10 to the negative 31. Okay. And then finally, taking the square root of all of that gives me a speed of 2.99 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters per second. All right. So that's the first half of the problem. And like I said, hopefully that was fairly straightforward. It was exactly what Chapter 25 was all about, introducing you to electric potential and how that is advantage because it leads to potential energy, which leads to conservation of energy, which leads to kinetic energy, which leads to velocity. So hopefully that is what you did first. B is a little tougher, and no doubt about that. It goes on to say, well, prove then that this is the equation. And it gives even a hint here. Maybe the best way to do is to think of this as a sum of a bunch of cones. I say that because, well, we had some homework problems where we took a bunch of, a sum of a bunch of rings. We did take a bunch of rings, and we had same size rings, and the same size rings ended up in giving us the potential from a hollow cylinder. And this is like that, except it's a cone. And there the radius is changing along with the position. But fortunately, they change together, so it's really only like one variable. So it kind of is like the cylinder. You'll see that in a minute. So I will use their hint. And you can see each radius has a bigger radius starting further away from the apex. When you start, it says here, start with the potential for a ring and then add up an infinite number of rings. It even helps us along the way here. The surface area of the sloped part of a cone, not the base down below, is given by this equation. Setting it up is worth a lot of partial credit. So I guess I'm kind of out of space there on that page. So I'm going to use the back side here of number 2 and begin by saying, okay, I want to find the potential for a cone. I can think of that as adding up an infinite number of rings. And maybe it's worth drawing a ring, and maybe I'll also just kind of put my cone flaring out along the x-axis. That way I'll be thinking about moving my integral from x equals 0 out to the end of the cone, knowing that this is going to be h, the height of the cone. So I'll just kind of turn it on its side, and that way I integrate with x. And I guess you don't need to. I guess one advantage of tilting it is you're kind of doing the traditional x-axis of adding up, and that may make you feel more comfortable. But the fact that you tilted it might make you feel uncomfortable, and I don't think adding up y's would be much of a problem either. So I tilted it. I'll go with it. I'm not sure if that was a better option or not. But again, in my mind, I just want to kind of illustrate that what I'm trying to do here is think of this first one as a ring and another ring and another ring and another ring. And I'll draw them kind of far apart. Here's the last ring. So they doesn't get too sloppy and look like they overlap. But of course, you can imagine it's an infinite number as I move along here. And so I guess my first step, as the hint says, is find the potential from a ring, which we derived in class and it's in your notes, or it actually wasn't real hard to derive, so you could start again. But I'm good with you starting with a ring. It's kind of the thinking behind it. And so if we jump back here to chapter 25, here it looks like it's example number 5. They take a ring and they get the potential of a ring where they say, okay, A is the radius of the ring and X is the distance out along the axis of symmetry. And after they do a couple of steps, they get right here. This is the potential. So that's good. Actually, this example goes a step further and then shows you the other reason why potential is nice, because when you take its derivative, you get the electric field. So this would be the electric field from a ring, which we also derived back in chapter 23. So they were trying to show you, and I did it in class, of how those are connected together here. But this is what I would want. Okay. And so I'll go ahead and maybe write that equation right here. So this is Coulomb's constant times the charge on the ring over the square root of a squared plus x squared. And the reason I wanted to write it here on the side is I just didn't want to, I didn't want to confuse some of the symbols that is in this problem with this one. For example, for our problem, the A and the X would be the same thing for our rings. So in other words, if I'm trying to get the potential right here for maybe this green ring, I'll darken it in right there. Its radius would be the same as the distance out. And so I would put each of these as an X here. So for our case, I could write this as 2x squared down below. And that might make things a little bit easier to think about. And also, capital Q, come back to the problem, was the total charge on this whole cone. So this equation represented Q on the ring. So maybe I would replace it with a kind of maybe a delta Q or something, just something to indicate it's not the whole charge on the cone. So if I kind of use that back up here, I get Coulomb's constant times a delta Q over the, and I'll just put square root of 2 times x to simplify that. And so that might kind of be the first major step. I'll then switch it into a calculus step by saying mentally I'm going to make each of these rings thinner and thinner and thinner so that there's something going to zero, something getting infinitesimally small in this equation. And I'll point out it's not x. If I think about this ring getting thinner and thinner and thinner, it's still at a position x. And of course, what does get infinitesimally small is the charge on the ring. So I'll write it as a dq of the ring. And this is the part I was saying when we did all these, when we were first introduced to them in chapter 23, but also here in chapter 25, where we're adding up a bunch of things. This could be the tough part of the problem, is there's 3 tough steps, and this first one right here is changing into an integral, and the second big step is then changing this, whatever became infinitesimally small in the equation, changing it into a dx, so I can put the limits, because I want this eventually to be a dx, because those are the limits of my integration. And so I need to match those together. In my mind, I'm going to take a limit along x, so I've got to have a dx. So I've got to change this infinitesimal small thing, whatever it is, in this case it's the charge on the ring, into an infinitesimally small distance. And so this game that we played on more than one equation was to say, let's look at charge density. And we had things like lambda for things in a straight line, sigma for things on a surface, and rho for things in a volume. In this case, since it's a cone, and the charge is spread out, maybe I should even make a cone here. But see, the charge is spread out on the cone. It's definitely then spread out over a surface here. Okay. So with that in mind, I'm going to use the sigma and say sigma is the charge of something, dq, spread out a little area. And when I say something, what I mean is it's the charge with the corresponding area. So in my case, since I'm talking about a ring, I would like this to be the charge on a ring. And so if I kind of draw this green ring here, so looking at it right here, here's my green ring, and I ask myself then, I want to get the charge on this green ring, okay. I need the surface area of that green ring. And if you can imagine then undoing it, it would be the length of it times its width. And so remember, it was all curled up a moment ago, and so its length is the circumference. So I'm going to replace the little bit of area of the ring here with the length of the ring. That would be 2 pi times its radius. Well, let me pause right there, times its radius. Remember that for our case, the radius of the ring is the same as the x position of the ring. So, again, if I kind of curl this back up, if this from the apex of the cone over, if this is the R here, the cone's getting all messed up. Okay, that's X, so is this. It doesn't really look like it in my cone, but I'm going to just write this then as a circumference as 2 pi x instead of 2 pi r. Because again, I'm trying to eventually get this into a dx, so it would be nice to put x's. So this is 2 pi r, this is the circumference. And then the thickness moving outward here, rolling it back up again. So I rolled it too much. Rolling it back up. Okay. The thickness would be along this distance, which is along the x-axis. But here's where you're going to be a little careful. And maybe you can see it here up at the top, or maybe I could draw a magnified picture of this cone. So here it goes across here. Here is the dx, but the surface area of the cone is kind of along this incline. So maybe I'll call it a ds, because this angled here would actually have a slightly larger length than dx. And so I want to be careful with that. I don't want to call this distance, along the slope the same as the distance along the center line. Now, clearly there's a mathematical connection to them, and I want to find that. But let me just call it a ds for now. And then use that back here. And so I'll take my sigma, and I'll bring this to the other side of the equation, 2 pi x ds. And that right here will be my substitution for what is the charge on the ring. Okay. Now, let's focus again on this ds. So maybe I'll just leave everything else alone. Although I got to admit, I'm tempted to do some canceling here because I see an x top and bottom. I see a bunch of constants. I want to pull them out. But let me just focus on this ds comment since I was working on this, that the area of the, slope part, the slope part of this cone is not the same as the dx. In fact, if I do an exaggerated picture, this would look something like here. This is the ds. And then this would be the dx. And in fact, this vertical piece, you might call it a dy, but we're working with a part where the slope is, 45 degrees. Because we're saying back here in our picture that each of these rings, the radius is the same as the distance out. So this is actually 45 degrees. And so I guess what I'm getting at here is the cosine of 45 degrees would be the adjacent over the hypotenuse. In other words, ds would be dx divided by cosine of 45 degrees. And that's going to help me now see what the mathematical connection is between a ds and a dx. There it is. And in fact, remembering that the cosine of 45 is 1 over the square root of 2, I can then say ds is root 2 times dx. Okay. And that could be an easy step that's overlooked. That this surface area of the ring, because it's, on a slant, is different than the length along the x-axis by the square root of 2. So ds is bigger than ds by this 41%. Remember, the square root of 2 is 1.41. So ds is bigger than dx by 41%. Okay, so again, that will help me back up here to put a square root of 2 times dx. Now, a bummer. It looks like all my scribbling, I've ran out of room here. So let me go to the back of page 3 here. So this is equal to, and so I'm trying to find the potential of a cone. And let me take all this stuff that's constant. Actually, let me cross out a few things on this page. And so square root of 2's cancel off. X's cancel off. Oh, that's going to make an easy integral. So it looks like step 3 of this problem is going to be the easiest part of it. And if I pull out my constants, I get Coulomb's constant, I get sigma. Sigma is the charge density. They said it was uniform. I get the 2 pi, and the only thing I'm left with now is an integral of dx. So there's the end of step 2, and I'll point it out again, as I've said many times in the lecture. Step 1 is changing it from algebra to an integral, and so you've got d something small. Then changing that something small into something I know what my limits are, what I'm going to integrate over, and this is the x-axis in this case. And so that was a big step right there, changing it from a dq to a dx. See, that way I can put my limits of 0 to h, coming back to this picture here that says I'm going to add up these rings from x equaling 0 to x equaling h. Okay. And then step 3 is going to be really easy for this one because it's actually do the integral. And sometimes integrals can be tough, but this one is pathetically simple. This would be just x evaluated from 0 to h. So that's just an h. Now, I would say we've got one more step to make, just like we've done in many of these problems, is it might be a good idea to then replace sigma with, where did we write sigma? Back here we said it was a little bit of charge over a little bit of area, but because it's uniformly distributed, it would be the same as all the charge over all the area. And so I'm going to do that now. I'm going to put all the charge and divide it by all the area. And this is where the helpful hint comes in. The area of a cone here is pi times r and then the square root of h plus r squared. But for our case, the r and the h are the same. So let me write this then as a pi h and then the square root of, and hopefully you can see it here. These are the same, and I'll just call them h's. This would be 2h squared. And so what would happen is this h squared, square rooted, would cancel with that h. The pi would cancel, And this 2 with a square root of 2 underneath it would leave a square root of 2. And so then I still have Coulomb's constant and a Q, and then downstairs I still have an H. Yay! So I got it. By the way, it just dawned on me, I tend to like to think of things physically, but if you're maybe a little more math-oriented, you know, here's a connection between, you know, the ds and the dx, and I went kind of through a picture here, a geometric picture, a physical picture of what's going on. But you could have easily have done the connection between a little area and a little bit of x here, because we're given this equation, and it would be like h is the x-axis here. And so I guess I could have said the total area would be pi, and again using that formula but replacing the r with an h, because for our case r and h are the same, and then replacing the h with an x variable. I could think of this as then an x, and then there would be the square root of 2x squared. So this would say that the area is the square root of 2 times pi x squared. And so, in other words, coming back to this geometric picture here, if I went out a distance x, this would be that surface area, and it would follow this equation. So if I took a look at how does the area change with x here, I guess I would have the square root of 2 times a pi and times a 2x. And maybe writing it a different way, dA then would be square root of 2. Actually, let me write that last. I'll write it as 2 pi x square root of 2. And the reason, and then the dx. And the reason that could have been mathematically helpful, that's essentially what I did here in this picture, right? I said a little bit of area, and I put 2 pi x, and I had a ds, but later on we said that that was the square root. So that would be a 2 pi x, and then the square root of 2 dx. So I could have done that substitution right there and put it in, and of course got the same thing. And that's where that 2 pi x square root of 2 dx comes from. It is a little bit of area. So I guess I didn't need to look at the picture. Anyways, but I digress. I don't really like that. That's kind of, you know, what you would do if I was teaching a math course. What is the connection between the full area and an infinitesimal piece of area? But that's not the goal here, to teach math. The goal here is to teach physics here. All right, but either way, hopefully that helps. I better get moving on. I've digressed, but let me look at my pace. So my pace is still great. Still under, 25 minutes a problem. Let's go to this one here. It says, study the circuit at the right. And then, of course, it asks for the charge, the voltage, and the energy on each capacitor. Again, I'm sure you anticipated this one coming. I talked about it, did a problem like this. The circuit was connected a little different. And so we talked about doing equivalent circuits. So why don't I do the equivalent of this? And this might be the hardest part, is to recognize that as electrons come off, they would hit this node, and some would go this way and some would go that direction. Then the ones that did go towards the 3 would continue on and go to the 4 and would continue on and go to the 2. So in other words, the 3, the 4, and the 2 are all in series. And so maybe I first would leave the 1 microfarad alone and then say what is the equivalent of the 2, the 3, and the 4. And given that they're all in series, my first calculation might be this, that the equivalent capacitance is 1 over C2 plus 1 over C3 plus 1 over C4. And as you saw me in class, and I'll do it again on my calculator, I like to enter them this way. These are the sum of the reciprocals, and then take the reciprocal of that. All right, so if I do a 2 reciprocal plus a 3 reciprocal plus a 4 reciprocal, hit enter and take the reciprocal of that, I'm thinking that the equivalent of those 3 is 0.923 microfarads. So I'll even put that in my diagram here, 0.923 microfarads. Okay, got it. Nice. So again, this is the equivalent of that one. And as you heard me say many times, equivalencies are nice, but only up to a point where they help us answer the real circuit. And in fact, you might even be tempted, but it's unnecessary, to say, well, wait a minute. Aren't those 2 in parallel with each other? So we can get equivalent of those 2 and what you might call the equivalent of all 4 of them. And again, since they're in parallel, you just add. So I'm just going to add a 1 to my 0.923. Okay? And so this is what I call the equivalent of the equivalent. Now, it may not be obvious, but this is really kind of a waste of time. I mean, yes, I could get the total charge on the equivalent one, but there's never a place in the problem where it asks for, what is the charge on the equivalent capacitance. It asks for the charge on the individual ones. And of course, the reason why I'm saying then this is not necessary is because once you get to this one right here, the equivalent, you might go, well, it's very clear that there's 10 volts on the number 1 as well as 10 volts on the equivalent of 2, 3, and 4. We don't really need to care that there is a 10 volts on the equivalent of the equivalent. Well, we could just stop right here and do kind of this first step and say something like this. We could say, all right, the amount of charge is then the capacitance times the voltage. And we can then use this equivalent circuit, and we don't have to go down to here. We can use this equivalent one to say, look, we could actually get the charge on number 1. It would be a capacitance of 1 times a voltage of 10. And it's micro. So this would be a 1 times a 10 coming out to be 10, and I guess microcoulombs would be the appropriate units. And again, looking at the equivalent one, not needing to go all the way down to here, I would do the same thing and say, well, how much charge is on this equivalent one? And again, it would be 10 times the capacitance. So maybe I'll put charge on this equivalent one because it would be the 0.923 times 10 volts, which of course comes out to be 9.23. And this would be micro and microcoulombs. All right. Now, again, there is no place in this chart that really cares about what's on the equivalent one. And like I said, that's the neat thing about equivalent ones and also the dangerous things about equivalent. I really don't care about what's going on the equivalent. I only care enough about the equivalence to see how I can use it to find out what's going on the real original circuit. But here's where it can be nice, because these are all in series. In other words, whatever charge went to number 3 also went to number 4, which also went to number 2. And so all of these have the same charge, and all of those would be the charge on this equivalent one. And hence, I just now have found the charge on number 2, 3, and 4. They're all equal to each other, and they're all the same as that equivalent one. So that's why that can be very useful. Oh, by the way, I should have put 10 right here. I kind of argued that. Now, here's where I would want to be careful and say, well, this is not a 10. This is the 10 volts on the equivalent, and that was useful to getting the charge so that I could trace it back to here. But the 10 on this equivalent is really the total voltage of number 3, number 4, and number 2. So all these 3 should add to 10. These 3 should add up to 10. So that's kind of good to keep in mind to see if I'm doing things right. But this 10 volts on this equivalent in by itself doesn't really help me here. But what it did help me do is get the charge on those. And then remembering that if you know any 2 of these 3, you can get the third one. Because remember, this is the mathematical connection between the capacitance, the voltage, and the charge. So just looking at this chart right now, I've got capacitance and charge. So I can get the voltage by taking the charge and dividing it by its capacitance. So I'll do that. The charge on number 2 is 9.23 microcoulombs. So if I divide it by its capacitance of 2 micro, the micros cancel off, and a farad is a volt, a coulomb per volt. So when I divide the 2, I get an answer in volts, 4.62 volts. And so there would be the way I would get the voltage here. Now, I should do that on down the list. And maybe just to save a few keystrokes, I'll multiply it by 2 to undo that one and get it back to my charge. But now I'm looking at the 3. So I'll divide by the 3. And so this should be 3.08. And then likewise, just to undo my division by 3, so I'm back to my 9.23, and then divide by the last capacitor of 4 would give me 2.31. Okay. So there it is, and if I add these together, 7, 8, 9, 9, yep, it adds up to 10. So that's good. These are in series, so the sum of these 3 should add up to 10. They should all have the same charge. Whereas this one is in parallel with the battery, so it should have a voltage of 10. So all that looks good. Now, the last step is to get the energy. We've got a couple of options. My favorite is 1/2 CV squared, but of course that also works with 1/2 charge times the voltage. It also works with 1/2 times the charge squared over the capacitance. So I'll do this one. And so in this case, it's 1/2 times the 1 times the 10 volts squared. And we're looking at 50, although let me be careful with my units. Remember then that this would be volts squared, but this is micro. And I put it in as a 1. So had I not had the micro, this would have came out to be joules, but I do have the micros, so I guess technically that is 50 microjoules of energy. And I guess I should put volts here. So I'll leave it as a 50, but I'll just label it with microjoules. Some of you might feel more comfortable writing it as 5 times 10 to the minus 5 joules. So either one is fine. So doing the same thing for the next line, 1/2 times 2 times 4.62 squared comes out to be a 21.3 in the units of microjoules. And again, you might feel more comfortable writing it as 2.13 times 10 to the minus 5 joules. And 1/2 times a 3 times a 3.08 squared comes out to be about a 14.2 microjoules, or 1.42 times 10 to the minus 5 joules. And one last time, 0.5 times the capacitance, 5, times the voltage, 2.31 squared, coming out to be about a 10.7. And so 10.7 microjoules. All right. And so that one hopefully went well for you. I know this material you had the least time to digest. So because of that, it might have been a little bit hard. But I think this material is easier than, this is from chapter 26, than the first 3 chapters we did. And hopefully you'll find it that way. And in fact, you'll see how number 5 fits into this, is because 26 is kind of divided into 2 pieces. The first is the scientific concept of what is a capacitor, and then the second part of it is using capacitors and the application of the capacitors. So this problem number 5 is about that scientific definition, and kind of goes through how we got the capacitance for the parallel plates. And the one we just did was actually then using the capacitors as either an let's see, we talked about capacitors as an energy storing device. We talked to them about a charge storing device. We talked about them as being filters. And we talked about them as being sensors. And so those are some neat applications. In fact, little heads up, on the next chapter, we'll use capacitors as a timing device. And so I told you as the semester went along, we would keep talking about what is the usefulness of capacitors. All right, well, I hope this one kind of helped with my description of what we did for the parallel plate. I have not gotten this far in the grading yet, so I have no way if this to indicate what the hard parts were for you guys on this problem. But it does kind of summarize of what we did in class and what your author did. Your author starts off with talking about the easiest capacitor, which is a parallel plate. So if you have, some electrons that you move from one side to another, you're going to get an electric field across here. And so to get the change in voltage, you just integrate the electric field. And to get the capacitance, then, the definition is just then the charge divided by the voltage. That's why we needed this step. And we don't really specify which side we're charging, positive or negative. That's why I didn't put like a plus or minus here. In fact, the capacitance is defined whether or not you charge it. I mean, you can have an uncharged capacitor and you still would say this is the capacitance. You don't have to have a charge on it. So it doesn't matter whether this one's positive or this one's negative or the other way around. Or it doesn't even matter if they have no charges on them. It's still a capacitor. So that's why like I said, deliberately. And you might not have seen these twin lead antenna ones. So I know some of you hadn't seen the coaxial cable, so I was glad I brought out the coaxial cable and kind of showed that. This one is just an antenna lead. And other leads here, but it's called a twin lead. And so it's just 2 side-by-side wires. And there's a certain capacitance. And we talked about in class how the capacitance in our coaxial cable can be a bad thing because of the timing device of it, the fact that it takes a while to charge it up. And so a lot of capacitance means that sending a digital signal through it is not good. But there's other really nice things about that coaxial cable, so we use them a lot. And the same thing here. All things are going to have a little bit of capacitance, and so in this case, sending a high rate data signal down them, capacitance is an unfortunate bad thing. But well, not completely bad, but I'll just say mostly bad because it slows down the data rate. But at the same time, we have to. I mean, there's always going to be some capacitance. So there's always going to be some charges and some electric field between them. All right. Anyways, I digress a little bit here. So let me come back to the problem. And the problem here starts off by outlining what we did in class. So that was a way, hopefully, to kind of prime you or pump, if you will, to kind of get you ready. And so that's what it says. It says, follow this outline to find the equation for the capacitance of two parallel antenna wires, which have a radius of capital R. They have a length of L. I guess I didn't show that in the picture. And their centers are a distance d apart. This is called twin lead antenna wires. Hint, the equation for the electric field outside of the wire is given by this. Oh, which, again, just trying to help you along there, but that does remind me of our discussion we had. Where was it? Where number 2, where I said, what is the field outside? And so there it is. E is proportional to 1 over R. And so that's what we're given here. So if I were to draw a picture of it, and I've been drawing electric fields in kind of a burnt orange. Let's see if I've got a burnt orange. This might be a good one. Maybe I'll draw it from one surface straight across to the other. So I guess indirectly I'm kind of saying that this one is positive and this one is negative. But remember, capacitance is a geometric thing, so they don't have to be charged at all, and it doesn't matter which way you charge them, positive or negative. But just so I have some kind of mental picture, which is, I should point out, is why we just do the absolute value of the voltage. It would be the same if you just switch the charges around. But I'm going to do this integration. So I would start this problem by saying, all right, the voltage here in absolute value would be the integral, and since I'm doing absolute value, I'm just going to drop that negative sign. The electric field, which would be lambda over 2 pi epsilon times R. And then I'm just going to go straight radially across, so this ds then becomes a dr, so this is a dr. You might even say there's technically a dot product, but again, I'm just going to go straight across, and so the direction I integrate is the direction of the field, so I guess that's cosine of 0 degrees, which is just 1, so we don't really need that as part of our equation. Like all integrals, we can factor out constants. It probably should be a little clearer in here that the charge will spread out evenly up and down. There's no reason that it's going to prefer one way over another. And so the charge per length along this direction is the same and uniform, so I can pull it in front. And I don't really say that, so I guess we're going to have to convince ourselves. Cut a line here and cut a line here, cut a line here. There's this line of symmetry here. So we're going to have the same uniform distribution. Now, it could vary along the circumference of it. That's a whole nother story in itself. But for simplicity, let me just say it doesn't, and it really doesn't matter for this calculation. So I'm going to just say it's uniform, and I'm going to integrate from here out to here. Okay, so this then would be dr over r. And maybe a nice little subtlety in this is, what are my limits of my integration? And we need to remember that the electric field is 0 inside a metal. So notice in my picture, I did not draw this electric field going any further than the surface of the wires. It started at one wire and terminated at the other wire. And so when I go to integrate, I only integrate where there's an electric field. Or maybe put another way, you could say I'm going to integrate from the center to the center, but the first part of it and the last part of it would have an electric field of 0. So the integral from 0 to capital R is looking like this, 0 times dr, which comes out to be 0. And the integral part from here, which if you call the center of it 0, and I guess we have to because we're using the electric field as measured from the center, I would have a limit of, and I guess this would be a d minus an r out to d. But again, the electric field would be 0 in this second wire. So that would be 0. And so what I'm getting at is you might be tempted to just say, well, I'm going to do an integral from 0 to d. But, like I said, the first part of it, 0 to r, will give you a 0, because you won't use this equation for the electric field. So I might as well just start my integration where there is a field at capital R. And then likewise, there's no point in going all the way to d, because that last part is 0. That is, d minus r to d is 0. So I'm just going to go to d minus r. And so this would be a lambda over 2 pi epsilon naught, and ln is what we get when we integrate dr over r. We get ln of r evaluated from capital R to d minus capital R. So this would be a lambda over 2 pi epsilon naught, ln of d minus r over r. All right, now with that said, I'll go ahead and finish the problem, and therefore finish the test, by saying the capacitance then, by definition, is the charge divided by the voltage. So I just did the voltage, so this would be a lambda over 2 pi epsilon naught ln little d minus r over r, okay? And then the charge, and of course I guess we do need to remember the definition is charge, but it's the charge on one plate, it's not the two together, which by the way might make you think that you have to have a charge on them to have a capacitance. You don't, because it's going to cancel off with the stuff on the bottom, and so it's kind of like having a 0 over 0. The ratio stays the same regardless of how much charge. In fact, that was even one of the discussion questions in the lab on capacitors. It says, does the capacitance change with different voltage or different charges? And no, it doesn't. And so I guess I would just do this. If it's uniformly spread out, it would be lambda then times the length L. And so you can see now the lambda is canceling off. Again, that's why the capacitance will not determine how much charge you actually have. You could have 0 charge on them and it still has a capacitance, or you could have a lot of them, or you could have plus or minus and then switched. Anyway, sweeping this around, this becomes a 2 pi epsilon naught in the top times an L and a natural log of this mess in the bottom. Just dawned on me, and I got a little careless because I did this whole problem with the electric field from only one charged wire. So the total voltage would be double that. because I would have the same field effect from the one that is negative. And in fact, that was our discussion for the parallel plates. For one plate, we had a sigma over 2 epsilon, and the other plate gave us the same amount, so we doubled it to come up with the total electric field. And we integrated the total electric field. And I forgot to mention that back here. So this would be, what I did was only one wire. I need to double it. All right, so then the 2's cancel off. So the final answer should be this very famous equation, at least for you electrical engineering people. This will become a very famous equation for you. Although, well, now that I say that, you'll probably work a lot more with coaxial cables than you will twin lead cables in today's world. But in my world of years gone by, this was a big one and an important one. This and the inductance. And again, the inductance is magnetism, so that's coming up. And we'll do the same thing. We'll talk about the capacitance and the inductance of a coaxial cable and a twin lead, and the advantages and disadvantages. All right, well, hope that helps. There's the test, and hopefully you graded yourself, and you also looked at any mistakes and use it as a learning opportunity, and we'll move forward. All right, take care, everybody.